Welcome to Sundar's lecture. This is lecture number 16. In this lecture, we are going to see universal gates. So, which are all the combination of gates, or which particular gate can be used as a universal gate, right? So, what are the topics we have seen in the previous class? See, these are all the topics we have seen. We have started with the logic gates. We have seen NOT gate, AND gate, OR gate operations, XOR gate, XNOR gate, and then we have gone for NAND and then NOR gate. Also, we have seen what happens if you give default 0 to 1 pin of XOR gate as well as 1 to 1 pin of XOR gate. And we have seen inverted input AND gate, inverted input OR gate, right? The operation of these two things. And in today's class, we will see universal gate. See, I have told you already, right? So, which is why we are calling a gate to be a universal gate. The reason behind, if a gate or combination of gate combination of combination of gates can perform can perform not, and maybe I will use a different color. The concept behind this one, not and or operations, then it is called universal gate. Can you understand? The concept behind this one is, so these three operations, not and then or the whole operation that can be performed in Boolean expressions. If you take any Boolean expression, you can implement the Boolean expression with these three operations. And if a gate can do these three operations, or a combination of gates can do these three operations, then obviously we will call that as the universal combination, right? So the first one we will write it down because we know everything already. Anyhow, we will write it down. Number one, the first one, the same gates: NOT gate, AND gate, AND gate, and then OR gate. This is one type of universal combination, right? These three can be performed by these. A combination of these three. Try to understand. Combination of these three. And second one, what I can write now, NOT gate, AND gate, not gate, AND gate, AND gate, OR gate, and XOR gate. XOR gate. Am I right or wrong? Why I am using XOR gate? Because XOR gate can perform what? NOT gate. That is what we have seen in the previous class. So this three combination is a universal combination, right, to understand, right? So the number 3 is very important. It is only NAND gate. It is only NAND gate. And the fourth combination, not combination, gate is only NOR gate. Right? So this is the idea, and we are going to see these two types because we know this one already. This one is not a major thing because you replace NOT gate with the XOR gate. That's all, right? So now what we are going to see. So what I have written, proof for NAND gate as a universal gate. So that is what we are going to see. Right. First one, we will take what we are going to do. NAND gate as NOT gate. So what I am going to do, I am going to perform NOT operation using NAND gate. That is my idea. See, what is the NAND gate symbol? We know, right? So what is the symbol of NAND gate? Symbol of NAND gate is this one. This is the symbol of NAND gate, right? We know this one. And what is the output equation? See, you know that one too, right? If this is A, if this is B, then Y will be is equal to A dot B the whole bar. So this is the equation we already know. So what I am doing now, let me do one thing. Let me do one thing now. Maybe if I draw like this, if I draw like this, what I have done here, I have made two input to a single input. Let this be A now. Let this be A. So the NAND gate will get A here as well as A here. Am I right or wrong? Right? So instead of B, what I am doing? I am just giving both A, both input as A. So what happens here? Y will be is equal to now. It is A dot A the whole bar. Am I right or wrong? Yes or no? A dot A, right? A dot A. What NAND gate will do? Two inputs will be operated, unoperated, and then it will take the opposite, inversion operation, right? So that is what we are getting here, right? So now what is this one now? What is this one? What is this one? We know, right? What is A dot A? It is A, right? A dot A is A. We have seen this is a law, right? So what we can write here? Y can be written as now what? A bar, right? So what happens here? A is given as input. This is input, and we are getting A bar as output. So what is this now? This is a NOT gate, right? By using an AND gate, by using a NAND gate, I have just made a NOT operation performed, right? So what I have done now, I have done the NOT operation with an AND gate. Now what is the second one now? Now I have to go for AND gate. I have to go for AND gate, right? So we will go to the next page. What is the thing? Second one, NAND gate, NAND gate as AND gate. How can you perform now? How can you perform? So what is the output of AND gate now? What is the output equation of the AND gate? So AND gate equation y is equal to, it is A dot B, right? It is A dot B. This is for AND gate, right? For NAND gate, what is the output? Y is equal to A dot B whole bar. This is the output equation of NAND gate. And what I can do now, I can draw the NAND gate. It will be easy to understand, right? Listen me very carefully. This is my NAND gate, right? So what I will get as input here, this is A, this is B. I have got A dot B now, the whole bar. This one I will get if I put a NAND gate. And what we can write now, we can write this equation to be A dot B whole double bar, right or wrong? Because bar can be cancelled out, and finally I will get what? A dot B. So for this, I have already got A dot B whole bar. To get another bar, what I can do now? Very simple. It is very simple. What you do now, you connect a short circuited input NAND gate. Only NAND gate. What is this one now? This one. What is this one? You are giving an input of A dot B. A dot B will be now again inverted. So it will be double inverted now. And what is this one actually? This is nothing but it is A dot B, right? So now I am giving A, B as input and I am getting output as A dot B. Then the whole combination will be AND gate. Will be AND gate. Can you understand, right? So what we have done now? We have performed the AND gate operation using AND gate, right? That is the whole idea. And what is the third one? This is very important. This is very important. NAND gate as OR gate. NAND gate as OR gate, right? So what is the output equation of OR gate now? Y, which is equal to A plus B, right? So this is the equation of OR gate, and we know Y will be is equal to A dot B whole bar. This is now NAND gate, right? NAND gate. So the idea, I have to make this A plus B to A plus whole bar, something like A plus whole bar or whole double bar or whatever it may be. I have to do something, right? So what I can do now, think about it. You have to do something to make this expression to dot bar, right? So what I can do now? What I can do? See, simply I can write y is equal to a plus b, right? It is there. I can put double bar now. I put myself. It will give you same result, right? So this one we know what is a plus b whole bar by De Morgan's theorem. De Morgan's theorem. Huh? What is this one now? What I can write this one? This one will be a bar dot b bar, right? So how I can write this expression now? I can write like a bar dot b bar. The whole bar is already there. Right now, you try to understand. I can, this is dot whole bar. This is one input of NAND gate. This is the another input of NAND gate. Am I right or wrong? Yes, yes, right? So what I can do, it is very simple. You don't worry about this one. Now you see, I have I have a NAND gate, right? I have a NAND gate. Simply, right? I have a NAND gate, and I have two inputs of NAND gate. Two inputs of NAND gate. What is the values of two inputs of NAND gate here? This is A bar, this is B bar, right? So if I give these two now, what I will get it down here? This is A bar dot B bar, the whole bar, right? How I can make? So I have here A and then B, right? A and then B. So what I can do now, I have to make this A to A bar. What is the procedure? You can draw like this, right? So now what is the simple procedure here? You draw from A, you draw a short circuited input NAND gate, short circuited input NAND gate, and you give it to here, so that this A becomes A bar. As well as here, what you do, you just draw a short circuited input NAND gate and you give this one here. So now what happens here? See this one. This is also NAND gate, this is also NAND gate, this is also NAND gate, and what is this expression? Now what is this expression? This one, which is nothing but I can write a dot b whole bar, can be written as what? A plus b bar. This a bar dot b bar can be written as a plus b whole bar and double bar. Already bar is there. So you can cancel these two, and finally what I am getting here, it is a plus b, right? So what is the thing here? I am giving input as a and b, and I am getting the output for a plus b. And what is this one now? It is an OR gate. So what I have done here, I have just implemented the OR gate operation by using only NAND gates. So now you see all these three, I have implemented the NOT gate using NAND gate, AND gate using NAND gate, OR gate using NAND gate. Then you conclude now. What is this one? This is a universal gate. This is a universal gate, right? Now what we will do? We will take the NOR gate, right? Now, so what we are going to do? We are going to prove NOR gate as a universal gate. For that, I am going for the same thing, NOR gate as the NOT gate. So what is the equation or diagram we know right for an OR gate? So this is the diagram for an OR gate, right? This is the diagram. This is the diagram for an OR gate. This is the input A and B. This is A, this is B, and Y will be is equal to A plus B the whole bar, right? A plus B whole bar, right? We know this one now. And for NOT gate operation, what I'm doing, I'm going to do the same thing, same thing. So this one, this one, and this one. Now again, I'm going to short circuit this two input. Give as input as what to say. This is A now. What happens now? Y will be is equal to A plus A the whole bar, because this is also A, this is also A. And what is this one now? A plus A is what? A plus A, which is equal to what? A, right? So simply I will get Y is equal to A bar, right? So what is this one now? What is this one? This is an OR gate. This is a NOT gate, right? So now I have performed the NOT gate operation by using only the NOR gate, right? What is the second one? It is very simple, right? So second one, NOR gate as OR gate. Now I am going for OR gate. What is this one? So what is the output equation for OR gate? It is y is equal to a plus b. This is for OR gate, right? I know this one. And I also know what is the output of this NOR gate. This is the output of NOR gate, right? So this is the output of NOR gate. So what I can do now, I can make this, if I want to get this one now, I can make another bar. So simply this one is same as the what we have done for AND gate using NAND gate, right? So I have done, I have, this is A now, this is B. Simply I will write it down. This is A and this is B. So y, which is equal to what here, a plus b the whole bar. What I have to do now, so this equation, to make this equation I can make plus a plus b double bar. So it is same like a plus b, right? So what I can do now here, simply I can put a short circuited input NAND gate. What will happen here now? What will happen? Y will be is equal to a plus b. Already it is bar here, so it makes double bar. So this is nothing but y is equal to a plus b. So what is this one now? I am giving a and then b and I am getting as a plus b. So this is now performing as OR gate. So NOR gate as OR gate, right? So both I have proved. Now what I have to do now? I have to go to the third one. Right now I have to perform NOR gate as AND gate. So what is the output of AND gate? It is A dot B, right? This is for AND gate. This is for AND gate. And the output equation of NOR gate, it is A plus B whole bar, right? A plus B whole bar. So this is for NOR gate. What I can do now? What I can do? What I can perform now? So I have to make this 2 plus bar plus the whole bar. What, this is the very simple equation. We have seen this one anyhow. So y will be is equal to, I am taking the AND gate expression and I am making double bars like this. So what I can write it down here, this one can be write as written as a bar plus b bar the whole bar. Why? Right now I got the expression like plus the whole bar, right? So now I can perform easily the NOR gate operation. So to perform this one, so I will draw here. See this one, what I am getting now, I am getting a NOR gate. I am getting a NOR gate here, NOR gate, and there are two inputs. There are two inputs, right? So what are all those two inputs here? It is A bar, this one, and then B bar. So what my NOR gate will do now? It gives as A bar plus B bar the whole bar. Now what I can do to make the A and B? So I already have here as A and then I have B. So it is very simple, right? So what you can do, you make this as now short circuited input for NOR gate. So it will come down here. And also for B you make the input short circuited input of NOR gate, right? So what is this one now? If I give A, it will come as A bar. If I give B, it will come as B bar. And if I give A bar and B bar input to the NOR gate, it will make this one like this. So what is this one actually? This is the final expression of y is equal to A dot B. That is what I have written here. So it makes now A double bar, cancel those two and you will get this one. So now you see this one. I am giving A B as input and I am getting A dot B as out. So what is happening over here? I am just performing the AND operation using only NOR gate. So what I can conclude now, NOR gate is a universal gate, right? So this is the final one, right? Now what we will do, we will take some examples and can implement with them with the implementation of gates, right? You see here, the concept is implementation of Boolean expressions with logic gates, right? What we have done in our previous classes, we have simplified the Boolean expression with the Karnaugh map, and we have written the simplified expressions. And what generally in the question papers or in examination point of view, they will ask you, they will give you an expression and they will ask you to simplify using Karnaugh map, and they will also ask you to implement them with the gates. And also the another one, they will ask you to implement them with only NAND gate, with only NOR gate. That is the whole idea. But we have not seen those kind of things in our previous classes, right? What we have seen, we have just simplified the equation and we have written the final expressions. Now what we will do, we will take a example number one. Example number one. So y which is equal to a bar b plus a b bar plus a bar b c, right? So let us assume that this is the final expression I have got from a Karnaugh map. I have simplified that and I am getting the expression like this now. So what I have to do here, I have to implement them, this expression with the gates. This is a 3-input system. Let it be 3-input system, 3-input system, right? So how will you implement this one now? Like, see, this one is a SOP function. It is a sum of product function, right? So now what you have in between, it is plus, right? So now you can do a 3-input OR gate. See, this is one input, this is one input, this is one input. So what I can do now, I can draw an OR gate, This is a OR gate, right? This is a OR gate. So it has 3 inputs, 1, 2, and then 3. What is the inputs of this one? So this is y. I can directly put this is y now. So this y will come here. Maybe I don't need to put this one. So what is this one now? It is a bar b. This one, first input. This will be a b bar, and the third one, it is a bar b c. And this is how you can put it down. So you add these three, you will get it as a output, right? These three. And what is this one now? It is a bar dot b. So it is an AND gate, right? So what I can do now, I can draw an AND gate, and I can give it down to this one. And what is the input of this one now? What is the input of this one? This is a bar and this is b. And same like I can put another AND gate here, another AND gate. What I can do now, I can connect like this, right? So what is the two inputs of this AND gate now? What is the two inputs of this AND gate? This is A, this is B bar, right? So now what I can do further? This one, I can put another AND gate, another AND gate. So what I can do now? I can just connect this one with the 3 input now, with the 3 inputs, right? Because it has 3 terms, right? So what is the inputs here? This is A bar, and this is B, this is C. Right, now what I have now with me, this is A, B, and then C. I have an input like this. I have input these 3 inputs, right? So what I can do now, I can just connect this A bar. How I see, I will take like this, right? Anyway, A, B, and then C. So what I can do now, I can put a NOT gate and I can connect this one here, and this can be connected directly here, and this can be connected directly here, B bar, right? So what I can do now, I can put a NOT gate and I can connect with this now. So this is A bar, so already I've taken A bar, right? So what you can do now, you can just connect this one and B. So straight away you give from here. C, this is connection, and C, you can straight away give this here. Right. Now, what is happening here? This expression has been implemented with the gates. This is how you need to implement an expression with the gates, right? So what we will do now, I'm asking you, you have to implement this gates with only NAND gate. How that is possible now? What is the possibility we can go with this? See, I will copy down this one to the next page. For example, say I have taken the same one to the next page. For example, in some questions they will give you an equation, a Boolean expression. They will ask you to simplify using Karnaugh map, and they will ask you also to implement the output expression with only NAND gates. See, we have implemented. No, if they are asking you like that to implement only with NAND gates, what you do? You generally draw this diagram. You generally draw this one. I will give you tips to how to convert this diagram into only NAND gate. So what I'm going to do, be very careful with this one. Be with me now. What I am going to do, I am going to mark this as now not. If I do so, I can map this also not, right? So what happens here? For example, you assume that I am getting A here. What it happens now? This A will go here without knots. Without knots. If I put knot here, so it become A bar, and again this become A bar, again it is a knot here, so A double bar, what will go as input in the Y of the first input, sorry, this OR gate first input, again A. So this knot will do nothing, right? So that what I am doing now, I am putting knot in all things, in all things. This is possible, right? This is the correct one. And what is this one now? What is this one? Tell me, what is this one? We have seen, right? See here, inverted input OR gate is what? It is an AND gate, right? So what I can do now, I can make this as a NAND gate, right or wrong? So this can be replaced with NAND gate. And what is this one now? These are all NAND gates. These are all NAND gates. And NOT gate, how to implement a NOT gate using NAND gate? That is what we have seen here, right? So NOT gate using NAND gate, what we have done? Just short circuit input and put like this. So what I can do now, I can rough it out. This one, what I can draw here, see here. This is also possible, right? So this one. Now I can rough this one as well. As well. What I can do now? Put like this. Put like this now. This one you connect. Right now, what happens now? Look into this one now. This is NAND gate, this is NAND gate, this is NAND gate, NAND gate, NAND gate, NAND gate. This is also an AND gate. I can replace this one, right? I can replace this one as an AND gate. So look into this diagram now. I have implemented this expression with only NAND gates, right? So this is how you need to convert an expression or implement the expression with only the NAND gates. Try to understand it very clearly, right? So what is the idea here? I will give you tip to do with only NAND gates. That is only applicable to the POS functions, right? That you do by yourself. It will be very easy to, right? So what are all the topics we have seen in this class? So we have started with the universal gates, and in universal gates what we have seen, these three operations should be performed, NOT gate, AND gate, and then OR gate, right? So what are all the topics we have seen particularly in this one? So universal gates, we have started with universal gates. What are all the combinations of universal gates? NOT gate, OR gate, and then AND gate. The combination of these three, and OR XOR, the combination of these three, and NAND gate, NOR gate separately can be taken as a universal gates, right? So we have seen the proofs for a NAND gate as a universal gate. First we have seen NAND gate as NOT gate, and then NAND gate as AND gate, NAND gate as OR gate, and then we have gone for proof for universal gate for NOR gate, right? So NOR gate as NOT gate, NOR gate as AND gate, and then OR gate and NAND gate, right? So OR gate, and we have seen how to implement a Boolean expression with only logic gates, right? So, and also we have seen how to implement them with only NAND gates, right? So this is what we have seen, right? So we will see in the next class. Thank you.